Find the general solution of the system of linear ordinary differential equations. So we have two ODEs. Now we need to solve. That means isolate x and y. So this system can be written in terms of a matrix system. So let's write dx over dt as x prime. So here goes x prime. This is y prime. So prime means derivative with respect to t, equals the matrix of the coefficients. So 2, -1 here. So 2, -1, 3, -2, and we can write xy. Okay, if we multiply these two, this matrix with this vector, then we get x prime equals first and y prime equals second. Now to solve this system, let's say this is our A, matrix A. We need to find the eigenvalues and eigenvectors. Okay, so Eigen Pairs. So let's find Eigen Pairs. That means eigenvalue and the corresponding eigenvector of A. For we do find the determinant of lambda times I, which is a 2 by 2 identity matrix. Okay, lambda I minus A equals 0. Okay, lambda I means lambda times I, 1 0 0 1, multiply by lambda, we get lambda 0 0 lambda. So that minus A is 2 -1 3 -2. When we subtract, we go by component. So that's determinant of lambda minus 2, that's first row first column, 0 minus -1 just 1, 0 minus 3 -3, lambda minus -2, lambda plus 2 equals 0. Let's find the determinant. So we just multiply these diagonal elements minus find this product. So lambda minus 2 times lambda plus 2 minus -3 times 1, -3 equals 0. Okay, let's solve this polynomial equation. So lambda minus 2, lambda plus 2, just FOIL, multiply. Lambda square plus 2 lambda minus 2 lambda minus 4 minus -3 means plus 3 equals 0. So we can cancel these two. So this is lambda squared minus 4 plus 3, that's -1 equals 0. Now we can factor this as lambda plus 1 lambda minus 1 equals 0. So from this factor lambda is -1, and from this we got +1. So we got two distinct eigenvalues. Next we need to find the corresponding eigenvectors. Okay, so let me go off for this. So let's find the eigenvector for lambda equals -1. So for lambda equals -1, so let me erase this. Okay, for lambda equals -1, so we have this vector lambda I minus A. So we plug lambda equals -1 here. So -1 minus 2, -3, 1, -3, -1 plus 2, that's +1. This times the vector V, let's say V1, V2. That's what we are trying to find, equals 0 vector, 0 0. And these two rows are always linearly dependent in these cases. So we can simply ignore second row, just work with the first. So multiply this with v1 v2, so we multiply this row to column, so negative 3 times v1 negative 3 v1 plus 1 times v2 v2 equals 0. Now this implies v1 v2 equals, we got infinitely many correct answers, but just take, let's say v1 equals 1. If we take 1 here, this becomes negative 3, and add 3 both sides, so v2 equals 3. So 1 3 is one of the many correct answers. Okay, so for negative 1 1 3 is the corresponding eigenvector. So eigenpair negative 1 comma 1 3. Okay, let's do the same thing for second eigenvector, which is lambda equals 1. So for lambda equals 1, again we go here, this matrix, plug in lambda equals 1. So 1 minus 2 negative 1 1 negative 3 1 plus 2 3. That, and unknown vector we are trying to determine, let's say v1 v2 again equals 0 vector, which is 0 0. Again these two rows are linearly dependent, so we just work on the first. If we multiply this way, negative 1 times v1 negative v1 plus v2 equals 0. Now we may take v1 v2 as, let's take v1 1, that means negative 1, move over, that means add 1 both sides, 1 1 1. Negative 1 plus 1 is 0. So 1 1 is the corresponding eigenvector for 1. So 1 eigenvalue and corresponding eigenvector is 1 1. Okay, so we got 2 eigenpairs here. Here is 1 eigenvalue, corresponding eigenvector, eigenvalue, corresponding eigenvector. Okay, and now we can write down the general solution. Thus the general solution is, for the first, which is negative 1 1 3. Okay, so e raised to negative 1t 1 3, that's one solution, and e raised to 1t 1 1 another solution. Two solutions and a linear combination, means c1 first solution plus c2 second solution. That's the general solution. We can say xy. So xt, if we read off the top, that's the x as a function of t, and y equals the bottom. Okay, that's the answer, final.